All right, the plan for today is to talk about 11.5 alternating series, maybe get a little bit into the ratio test or maybe save that for Wednesday's class. Obviously, we have the eclipse today, so my plan is to break a little bit early just to give a little bit of a buffer in case you want to get at, wherever you want to get to for the eclipse. So probably break around 1 or so, just depending on where kind of a nice break point will be. So um, I don't want to keep you too close to the time that it's supposed to start. I think it's like totality is somewhere a little after 2 o'clock or so, or at least the maximum amount of totality, whatever you want to call it. So, um, so planning to keep it, give you about an hour buffer at least there. So the quotes of the day today in honor of the candidates chess tournament going on right now, where a bunch of the top players in the world are competing for the spot where they'll challenge the current world chess champion Ding Liren. So a couple of chess quotes from Emanuel Lasker, the second world chess champion, held the title for quite a long time in the early 1900s. When you see a good move, look for a better one. Or from the current GM, Maurice Ashley, not the current GM, but a current GM, is alive and I think still competing today. Maybe fairly recently retired. There are 3 types of trades: forced, fantastic, and foolish. If it's not forced or fantastic, it's foolish. So I think both of these kind of hit on the same maybe underlying theme of, if you're going to make a big decision, spend some extra time, really think it through, and don't go wantonly into to big decisions, or just making a decision because it feels like it's kind of the easier path. Sometimes it feels easier just to say trade off the queens or something early, because that's one less thing for you to worry about in your opponent's camp. But again, if it's not forced or fantastic, if you can't say making this trade is really good for me, maybe at least according to GM Ashley, it's a foolish move. So I think this applies to a lot of things in life, right? Like when you're deciding what job to take for your first career job, or whether to go for a promotion or to switch careers or whatever it may be. For big life-changing events like that, make sure to think it through. And obviously these apply to chess more directly as well. Okay, so let's talk about then alternating series. So section 11.5, alternating series, main focus of today. We probably won't get all the way through the ratio test, but we might touch on it or we might not. So an alternating series is, well, roughly speaking, it's a series whose terms alternate sign from one term to the next. Or written more formally, it's a series that can be written as either sum n equals 1 to infinity of -1 to the n times a sub n, or -1 to the n plus 1 a sub n, where a sub n's are positive. So where each successive term alternates sign. We have a positive term followed by a negative term, followed by a positive, followed by a negative, and so on. And we have a theorem, the alternating series test. I almost kind of in a sense wish this test didn't exist, because it can be kind of confusing. So let's come off to the side here and just remember our previous test, or sometimes it's called a criterion, the divergence test, or sometimes called the divergence criterion or criterion for divergence. And we said the following. We said if, so here we have some, since I've already used ANs up here, let me just call this some BN. If BN does not go to 0, then the series diverges. And we said be very careful. If BN does go to 0, we actually, according to the divergence test, if BN does go to 0, we can't say anything about the series. The divergence test says nothing about what happens to series when the terms do go to 0. Sometimes they go to 0 fairly slowly, like say the harmonic series, and the series still diverges. Sometimes they go to zero very quickly, say like a geometric series, maybe 1/2 to the n, that goes to zero very quickly and converges. So just knowing that the terms go to zero and that's all is not sufficient to say it converges. In other words, it does not imply converges. But saying that this statement does not imply convergence doesn't mean that it does imply divergence. So just be very careful with the logic here. However, we have the alternating series test. Right, OneNote is being a little goofy, but looks like, okay, the alternating series test. Here we say if we have an alternating series, if the absolute values of the terms, these a sub n's, are essentially decreasing or technically non-increasing, and if they limit to zero, then the alternating series converges. So what we kind of have is a kind of converse or opposite. I would have to think for a minute, but we have kind of an opposite to the divergence test here. If we have an alternating series where the absolute values of the terms are non-increasing and the terms go to zero, then we converge. So this criterion here, coupled with the other two criteria, alternating series and non-increasing absolute values of terms, that is sufficient for convergence. So we have kind of a statement like this, but very important that this only applies to alternating series. So if we have some other random series, this theorem doesn't apply. It's only if we have an alternating series and these two criteria are met. But let's look at the alternating harmonic series, a famous series. Sum n equals 1 to infinity of -1 to the n plus 1 times 1 over n. Or it's like the harmonic series, but where all of the even number terms are negative instead of positive. 1 minus a half, plus a third, minus a fourth, and so on. Note that the alternating harmonic series converges by the alternating series test. We see clearly this is an alternating series. And we see that our an is 1 over n. We see this does go to 0. And we see that, of course, an plus 1 over n plus 1 is, of course, less than 1 over n, or an. This is a decreasing series. It's certainly non-increasing. So criterion, I guess, 1 and criterion 2 are both met. This is an alternating series. And therefore, we can conclude that it converges. Interestingly, this converges to, I think, log 2. So it's kind of random that it converges to such a number, but it does. If we look at another example, say something like this, we might be looking at this trig function and thinking, is it kind of an alternating series? Sum n equals 1 to infinity of cosine of b plus n pi, which is cosine of b plus negative cosine of b plus cosine of b plus negative cosine of b. This is an alternating series. But note that it does not converge. Well, I suppose except in the special case where cos b is 0, because then we just have the sum of a bunch of zeros and all the partial sums are 0. But if cos b is not 0, if this is not 0, this series diverges. Why is that? Well, think of my partial sums. My first partial sum is cos b, a number that's not 0. My second partial sum is cos b minus cos b, or 0. My third partial sum is cos b. My fourth partial sum is 0. My sequence of partial sums just keeps flipping back and forth between two distinct numbers, 0 and cos b. So of course the limit doesn't exist. I'm always going to be at least 1/2 of cos b away from whatever limit that I might propose, and one of the next two elements of the sequence of partial sums. Does this contradict the alternating series test? Well, it is an alternating series, but note that the terms cos of b in absolute value do not go to 0. So criterion 2, even though we do have an alternating series, criterion 2 does not hold. And therefore, we can't apply the conclusion of the alternating series test that the series converges. So this does not contradict the alternating series test because one of the criteria does not hold for the series. Even though it is an alternating series, not all alternating series converge. Just the ones, well, I shouldn't say just the ones, but under the alternating series test, it only applies to the ones that also satisfy these two criteria. Okay, does this series converge? Sum n equals 1 to infinity, -1 to the n over root n. Let me zoom in here a little bit with all these powers and radicals. It's a little bit small. Well, I do notice that this is an alternating series. Here my an is 1 over root n. I do note that my ans go to 0. Do I have a non-increasing function? Well, I know that the square root function is an increasing function, so square rooting a bigger number gets me a bigger output from the square root. And when that's in the denominator, if I put a bigger number in the denominator, it gets smaller. So this is a non-increasing function. It's a decreasing function, in fact, that goes to 0 in an alternating series. So yes, this does converge. Yes, by the alternating series test. So this was criterion 1, and this was criterion 2. And we do have an alternating series, which is essentially criterion 3. So those three criteria are met. This does converge by the alternating series test. Even though, note that 1 over root n gets small even slower in a sense than 1 over n. Right? The denominator is an even smaller number than n for large n's. So note that 1 over root n, this series diverges. This is a p series with p equals 1/2. One really nice thing about the alternating series is that we have another theorem. Let me zoom back out here. The alternating series estimation theorem. We've talked a little bit now in a couple of these sections, the integral test section, the comparison test section, for instance, where we said sometimes in series, we're kind of in the abstract world. We're asking, does this converge or not? And if we get an answer, yes, it converges, we kind of just say, good, it converges, and leave it there and move on. You know, it seems like we should try to get some kind of a sum. If we say, yes, it converges, can we get an estimate for what the sum is? Well, if we have a geometric series, we can get the sum for convergent geometric series. We have a formula for that. If we have a telescoping series, we could get the sum just by looking at the sequence of partial sums and getting its limit essentially by brute force. But if we get an integral test that says the series converges, that doesn't really give me an estimate of the size of the series or the value of the sum of the series. If I the same thing with comparison tests, that really doesn't give me an estimate of the sum of the series. Maybe it gives me some kind of bound, or maybe it gives me some kind of estimate, but I really, even if I say that I think that might give me an estimate, I don't have really good bounds on the error. So if I have an estimate, an approximation with no idea of how much error there is, that's not really an estimate, is it? I mean, I could, if those are my criteria, I could just estimate everything as equal to 0 plus or minus some unknown margin of error. I really want a margin of error to go along with an estimate to really call it an estimate. So, I mean, geometric series, like I know the exact value for the convergent ones, but if I want to make an estimate, what can I do? Well, the alternating series estimation theorem actually does that. It gives us a way to estimate the value of the series with a bound on the error. And that's really the important part, the bound on the error. We can estimate the value of any convergent series by just adding up the first bunch of terms, the first 1 or 5 or 10 or 1,000. But if I don't really have a good idea of what my margin of error is in any estimate, you know, the value of that may be pretty limited. I'm just kind of guessing at that point. But the alternating series estimation theorem says, with the same 3 criteria that I saw above for the alternating series test, that my series is an alternating series, the terms in magnitude are non-increasing, and the terms limit to 0. With these same 3 criteria as before, then the absolute value of the remainder, where S equals Sn plus Rn, the absolute value of the remainder, or the error in estimating this sum by the nth partial sum, is bounded in magnitude by, well, what is this? Sn is the sum of the terms up to and including an. So the first term that I leave off is an plus 1. The first term in magnitude that I leave off is an plus 1. So what our theorem here says is that our error in estimating the full sum by the nth partial sum, by the sum of the first n terms, is bounded in magnitude by the size of the first term left off. That's super nice. That means if I compute, say, the 10th partial sum, the sum of the first 10 terms, I can get an idea of how big the error is. It's no bigger than the magnitude of the 11th term. Again, assuming that these criteria are satisfied. So I just need to compute one more term than what I'm computing to actually estimate the sum. And that one more term gives me the error bound. So that's really nice. The downside is that error bound might not be a super sharp bound, right? We're saying that the error is no more than that number in magnitude. But if that number is a huge number, you know, that might not be super helpful. If I'm targeting a certain error, if I want an error less than or equal to this amount, the number of terms I might have to add up might be quite large for some of these alternating series. So let's look at a couple of examples. So let's consider this series, this sum minus 1 to the n over root n. We just saw that converges by the alternating series test. It met the criteria for the alternating series test. In other words, these 3 criteria. And we might just be interested in asking how many terms of the partial sum must be added to estimate the sum correct to 1 decimal place. If I want to get 1 decimal place correct, if I want to get point something and have that something be the right number, my error has to be no more than 0.05, right? So that it stays within, you know, if my estimate would say 0.1, then my actual sum has to be between 0.05 plus a tiny bit and 0.15 minus a tiny bit to stay where I would round to 0.1. So I'd be accurate to 1 decimal place. Right? So I go kind of a half of the next decimal place up and down. So I need my absolute value of the remainder to be less than or equal to 0.05. But, and this is 1/20th, right? But that means that an plus 1 has to be less than or equal to 1/20th, because my absolute value of the remainder is less than or equal to an plus 1. Again, very important that we had previously checked that all of these criteria are satisfied. So I'm not rechecking that here. That was work that we had just done. But under that check of the criterion, we see that that means that an plus 1 has to be less than or equal to 1/20th. Or in other words, 1 over root n plus 1 has to be less than or equal to 1/20th. Or I actually need at least 399 terms to be accurate to one decimal place. Remember, I said this 1 over root n kind of has even worse behavior in a sense than the harmonic series. The harmonic series terms go to 0 pretty slowly. And this 1 over root n, these go to 0 even more slowly. So we have to add up a whole bunch of these terms to get even one decimal place of accuracy because of how slowly they go to 0. So we're kind of bouncing back and forth around the limit quite a bit, right? Our terms don't get small in magnitude very quickly at all. We have to add up a whole bunch of them before we're even with it, even accurate to one decimal place, even within 0.05 of the true answer. So what if I wanted to find the sum of this series, sum n equals 1 to infinity of minus 1 to the n over 2 to the n, correct to 3 decimal places? This probably seems like a pretty big ask. I mean, I just said for one decimal place, we need, for this example, we needed 400 or so terms. 3 decimal places, geez, that's 100 times as many, or sorry, 1/100th of the, that's 1/100th of the error. If this guy scales like 1 over root n, if I want my denominator to be 100 times as big, I would need n to be like 10,000 times as big. Am I going to need like 400 times 10,000 terms? Well, I do notice that this is a different series though, right? This is actually a geometric series. So let's come off to the side, and we're not going to directly answer the question yet. I mean, I suppose maybe in a sense we will, but we're not going to answer the spirit of the question yet. We note that this is a geometric series. We could write minus 1 to the n over 2 to the n as minus 1/2 to the n. And I can note that this is sum n equals 0 to infinity of this minus 1, right? Where this series is all together, and then we have a minus 1 afterwards. I started with n equals 1 up here. So I just added in the n equals 0 term to make it a full geometric series. But the n equals 0 term is just 1. So I just added 1 to the beginning of every partial sum. So if I subtract 1 off, that's no problem. I'm not adding random stuff in the middle of an infinitely long series. I'm only adding one piece to the front and then subtracting it off. That's not going to affect any of my partial sums. But I noticed that this is a geometric series with r equals negative 1/2 that is in negative 1 to 1. So this is a convergent geometric series. It converges to 1 over 1 minus r. And then I can't forget my minus 1. So this is 1 over 1 plus 1/2, 1 over 3/2, or 2/3 minus 1 is negative 1/3. So correct to 3 decimal places, negative 0.333 is what I'm looking for. So in this case, I actually see I can find exactly my answer. But let's use the alternating series estimation theorem here, because we do have an alternating series. An equals 1 over 2 to the n. So if I want to be correct to 3 decimal places, I need, so 0.05 would get me 1 decimal place, 0.005 would get me 2, 0.0005 would get me 3. Or in other words, this is 1 over, well, 1 over 20 gets me 1 decimal place, 200 gets me 2, 2000 gets me 3. And oh, and this I want to set equal to an plus 1, just like I did up here. And an plus 1 is what? It's 1 over 2 to the n plus 1. Let me get myself a little more room down here. Or so I want, what? 2 to the n plus 1 bigger than or equal to 2000. If I log both sides, let me just bring up the calculator here. I know this is off screen, but I'm just gonna, I have n plus 1 log 2 bigger than or equal to log of 2000. And what does this tell me? N bigger than or equal to log of 2000 over log 2 minus 1. So log 2000 over log 2 minus 1. And this is about 9.97 or so. So I need about 10 terms. And this is really kind of showing the difference between a geometric series and one of these kind of, you know, what we're going to have a more technical name for it in a bit here, but one of these series that kind of barely converges in some sense, right? If this wasn't an alternating series, this would diverge. If this wasn't an alternating series, it would still converge. And I think this is just a really illustrative point. I mean, we didn't prove anything about, these kind of, series that only converge when they're alternating, but I think this just illustrates the point. 400 terms to get 1 decimal place of accuracy versus 10 terms to get 3 decimal places of accuracy. How quick the convergence is, how quickly these terms go to 0 for these ones that converge very nicely, like geometric series. And here, let me switch my share really quick. And because I don't want to type a whole bunch of stuff into the calculator, I just really quickly made an Excel spreadsheet here. I have the sum, the actual sum, 1 over 1 minus negative a half minus 1, negative a third. And we see our partial sums here. Here's the first partial sum, the second partial sum, the sum of the first 2 terms, the first 3, 4, 5, 6, 7, 8, 9. Sum of the first 10 terms. I see we go from rounding to 0.334 to rounding to negative 0.333. And it seems like we basically stay at 3 3s from that point forward. Maybe this next one's a little wonky, it looks like, but we do notice that it just barely works out. 0.33349.6. So it does barely work out. So we do see that from the 10th partial sum on, it seems like we do have at least 3 3s after the decimal point. And from that point on, the partial sum is not going to get any further away from the sum than 0.001. Okay, any questions on any of this? All right, let me just close this Excel file. Zoom was unhappy that I had that window open for some reason. So there we go. Okay, so again, alternating series, not a huge section, but when you do notice that a series is an alternating series, this gives you a couple more tools to use. The alternating series test for convergence, and then under those same criteria, being able to estimate the sum and get an error bound. Even if it's not a super tight error bound all the time, we do get an error bound, and that's something that's super nice. So moving on to 11.6, this is a pretty important section. Here we have absolute convergence and the ratio test. So we have a couple of definitions. We say that a series, sum n equals 1 to infinity, or n equals 0 to infinity, whatever, a sub n, is absolutely convergent if the sum of the absolute values converges. If I replace all of the terms by their absolute values, and the series still converges, then I say that the original series was absolutely convergent. And we say, oh, this got a little jumbled up over here. There we go. We say that a series is conditionally convergent if the series itself converges, but the sum of the absolute values diverges. So note that some series, like say this one, are absolutely convergent. If I replaced all of these terms by their absolute values, I would just get some 1 over 2 to the n, or 1/2 all to the n power. That's a geometric series with a ratio in -1 to 1 that still converges. The sum of the absolute values converges, therefore the original series converges absolutely. But if I look at, say, this series, sum -1 to the n over root n, or if I look at, say, the alternating harmonic series, both of those series themselves converge when they're in their kind of alternating state. But if I looked at the sum of the absolute values, if I got rid of the alternating bit, if I got rid of this -1 to the power, then 1 plus 1/2 plus 1/3 plus 1/4, so on, is just the regular alternating series, or sorry, regular harmonic series that diverges. Same with this one down here. Sum n equals 1 to infinity of 1 over root n, 1 over n to the 1/2 power. That's a p series with a p less than 1 that diverges. So those would be conditionally convergent series. We have a theorem that says if a series is absolutely convergent, then it's convergent. But again, the converse is not true. A series could converge, but not be absolutely convergent. It could be conditionally convergent. Take the alternating harmonic series as an example. And a second note, if the kind of original series over here only consists of positive terms, there's no difference between that series and the sum of the absolute values. So any positive series, which, remember, that was the criteria for a couple of our previous tests, like the integral test, the comparison tests, we had to have positive series. In those cases, when a series consists of only positive terms, well, regular convergence and absolute convergence are the same thing there. So if we prove that a positive series converges, then kind of for free, in a sense, we get absolute convergence of that series. But if we've got some positive terms and some negative terms floating around, that's whenever we can get a conditionally convergent series. And as kind of a side note, a negative series, a series consisting of only negative terms, is basically the same as a positive series, right? Think of the sequence of partial sums. You could just factor out a -1, pull that all the way out in front, and then you have a very similar convergence question for that sequence, right? So a strictly negative series where every term is negative, in that case, actually, convergence and absolute convergence are also equivalent. Where that equivalence breaks is when we have a mix of positive and negative terms, and really, it's even if I had, like, in my first 100 terms, some were positive or negative, but from term 101 on, all were positive, or maybe from term 101 on, all were negative. remember, convergence is like a property of the tails. So in that case, even because the tail looks like a positive series or looks like a strictly negative series, we still get the two are equivalent. So really, this conditionally convergent idea really only applies if I have like infinitely many positive terms and infinitely many negative terms, where no matter how far I go into the series, I still see a bunch of positives and a bunch of negatives still left over. Okay, so um I think I want to save this till next time because I want to use this motivate. We could probably get through the motivating example, but not talk about the ratio test. We're going to use the motivating example to motivate the ratio test, which is quite an important test. So I think we're going to break here and pick up with this example next time, talk about the ratio test, and then move on from there. So any questions on anything?